Okay students, it's we are now going to consider about the physiochemical process having during the iron extraction inside the blast furnace. It's hope you could remember that in the earlier part 1, from that you learned that at the bottom of the blast furnace you blow hot compressed air. So then at the top it's you fall that mixture of solid or coke and limestones having in it. So it's at the bottom with this hot compressed air, it's having oxygen there inside. It would start burning this coke coming to the bottom. Then it starts this reaction. It is coke get burned in that air in oxygen giving carbon dioxide. So it's a compressed air stream you pass, you blow. It's you blow air, that's why we call it blast furnace. It's this blast causes it, names it blast furnace. Okay, then students, it's when you blow hot compressed air, it is this reaction is having high, means in a large extent. All of the oxygen there in this air will be consumed for this reaction. It is you need to make that sure the flow rate, you need to optimize the flow rate at the bottom when you blow hot compressed air. It is anyway an exothermic reaction. It is minus 393.5 kilojoules per mole, the heat amount by 1 mole it releases. Then students, this huge amount of heat means more and more coke would get burnt here as all the oxygen would be used up there. So it would give you a lot of heat. This heat amount, huge heat amount would maintain the bottom temperature maximum. It's at around 2000. It maintains there. So in degrees of centigrade it is 1700, 2000 Kelvin. Okay. Then students, you need to make that sure it's that fast, this combustion reaction giving this heat amount consistently. As to make that sure, you need to optimize this flow rate as well as the flow rate here when you drop those solid mixture. And you need to maintain these particle size optimally. Then it is you need to maintain the composition there in this mixture, coke amount there, as well as coke particle size there, as well as the flow rate there, as well as the hot compressed air, the flow rate of that stream. Then you need to optimize as you get the desired combustion there at the bottom, maintaining it this high temperature there. And it's another thing, it's you need to maintain this coke amount as it is more than of the required for this reaction. It is, I will going to explain that soon. Why is that? I told that thing. So this coke amount you provide there, it shouldn't just sufficient for this reaction only. It's you need to provide more and more coke as to make that sure all the oxygen is completely reacted, and further other part of oxygen, coke, would involve in further reaction of ferrous oxide. We'll show you that soon. As well as it will be further forming carbon monoxide, which is giving our driving force, reduction force required for our future reactions. Anyway, so this is now very high, the temperature. When it comes down, this solid mixture is having still further coke, non-reacted, still all the oxygen has got rid anyway. So then remaining coke does not have enough oxygen to react and form carbon dioxide to get burned. Therefore, that remains as it is, as coke. That coke is at high temperature. You could find it being red hot. Students, this red hot coke, when it touches with carbon dioxide, there will be another reaction starting. Anyway, all of a sudden, with the exposure this air there having oxygen there in it, or more, all the oxygen was got used up, forming carbon dioxide. It's a sudden increase of carbon dioxide you get at the bottom. Carbon dioxide amount there at the bottom would get increased suddenly. Then there would be red hot coke touching this carbon dioxide. It would then start forming carbon monoxide. So it's an endothermic reaction. 172.5 kilojoules per mole. The enthalpy change. Anyway, it's very high, the temperature at the bottom. So if you could apply this equation, thermodynamical equation, delta H equals delta G equals delta H minus T delta S. Though this is positive endothermic, it is at this number of gas molecules here at the left side 1. At the right side, the number of gas molecules is 2. 1 becomes 2 means the entropy change is positive. Entropy gets increased. This is a positive value. So the product here would be also positive. Then at high temperature, it would be highly positive. This value into negative, it's a negative value, would exceed this value. Therefore, students, at high temperatures only, this would be spontaneous. This reaction would take place there. So, all of a sudden, as I have told already, carbon dioxide amount is going to increase. Then carbon dioxide start reacting with this coke, and all those carbon dioxide would gradually transform into carbon monoxide. Having this reaction at this very high temperature, temperature also favors this reaction. According to the equation here, though it is endothermic, this entropy change is positive due to the number of gas molecules increase during the reaction. Therefore, at high temperatures, this gives you a negative value. Therefore, it's a spontaneous reaction having at high temperatures. Therefore, students, you are going to have carbon monoxide being formed. Those formed carbon dioxide will be gradually transformed into carbon monoxide at the bottom. Then it is this carbon monoxide formed only is going up, means its carbon dioxide will be transformed into carbon monoxide, and this carbon monoxide is now going up. This carbon monoxide provides our driving force to reduce those iron oxides. It would be reducing there while going upward, touching with this mixture having iron ore there. It would reduce that iron ore into iron finally. Then, as I have told you, maintenance of this high temperature at the bottom is very important. It's roughly 1700 degrees of centigrade. So, ions, pure ions, melting point is at around 1538. So, therefore, it's above that temperature. Therefore, what you get, the iron form would be in its liquid state. Therefore, you could maintain iron at its liquid state, maintaining this high temperature at the bottom. It's an advantage, another advantage you get there. Then, students, when you compare the stability of carbon monoxide and carbon dioxide, I could prove you that the stability of carbon dioxide at low temperatures would be high than high temperatures. Or let's say the stability of carbon dioxide would be high at low temperatures. The stability of carbon monoxide would be low at low temperatures. Then the stability compared to carbon monoxide, carbon dioxide stability is the same, but compared to carbon monoxide, carbon dioxide stability would be low at high temperatures, as well as carbon monoxide stability would be high at low temperatures. Then, for that reason, though you have got a huge amount of carbon dioxide being formed there at the bottom, it's a very high temperature you get at the bottom. Therefore, it would gradually turn into carbon monoxide, which is more stable than carbon dioxide there. Then with going up, the temperature gradually would get decreased. At low temperatures compared to this, it is a low temperature. At lower temperatures compared to carbon monoxide, carbon dioxide is more stable. Therefore, its tendency is there transformation of this formed carbon monoxide into carbon dioxide. So let's find it out how and why this carbon monoxide and carbon dioxide's relative stabilities are in that way. Then after we could easily find it out the reason for reduction force provided by carbon monoxide transforming into carbon dioxide. Let's find that out. Okay, students, if we start thinking that carbon monoxide and carbon dioxide both are formed by the reaction of carbon coke with oxygen, it's just for the comparison only, comparison their stabilities of carbon monoxide and carbon dioxide only are doing this. Otherwise, it's not, I'm telling that these are the reactions having their bottom or somewhere. It is, I'm just comparing now their stabilities, their relative stabilities of carbon monoxide and carbon dioxide. Anyway, if you are about to form carbon dioxide using coke and oxygen, so you would find this enthalpy change being negative. You already know it is minus 393.5 kilojoule. It's negative. And its entropy change. It is a gas. So one molecule, there would be an entropy change, but not that significant entropy change. So it's close to zero, but I'm not telling it's zero. Anyway, you would have an entropy change. It's anyway not that significant as you get when number of gaseous molecules get changed. Here the number of gaseous molecules would be the same. Therefore, the entropy change would not be that significant. Therefore, according to this equation, the thermodynamic equation, delta G equals delta H minus T delta S, with what we use to compare their stabilities, thermodynamical stabilities. So, it's anyway, exothermic reaction makes that negative, and whatever it is, it's a very small value. Therefore, this product would be small. Whatever the temperature, it's not going to be that greater, the value product here, for the reason this is a very small value. Then at different temperatures, it's not going to get changed significantly. Therefore, anyway, whatever the temperature, it would be maintained at the same negative value, means closely. So there will be a slight impact by this, but it's not that considerable, the impact. Therefore, the stability remains same, whatever the temperature is. For carbon dioxide, I am saying now. Okay, let's do the same thing on carbon monoxide. Let's assume carbon monoxide is formed by the reaction of coke with oxygen. So, students, you get imbalancing 2 here. Okay, so 2 here. So the number of gaseous molecule is 1 and 2 here. Therefore, there is an entropy change. It is a positive entropy change. You could find that out using balanced chemical equation. If you get such entropy change being given by the balanced chemical equation changing varying number of gaseous products and reactants. So, it's then a significant entropy change you get. Compared to that, it's a significant entropy change. Then students, this is anyway the partial combustion of coke. So, that also is a negative. The enthalpy change also is a negative value. Then when you apply this thermodynamical equation, delta T equals delta H minus T delta S, this is negative but not as much as of here. So this is positive. Being positive here the value significantly, when you multiply it with the temperature, it would be further positive, and multiply that by negative, it would be negative. Then students, students, at very high temperatures, it would be very high, this negative value. Therefore, the stability or delta G value would be highly negative at high temperatures for carbon monoxide. So, for carbon monoxide, you get a very high delta G value, negative delta G value at high temperature. Compared to that, carbon dioxide delta G value at the same high temperature would not be that significantly changing, would not be that stable. Then we are talking about relative stability. Compared to carbon dioxide, at high temperatures, carbon monoxide's relative stability is very high for this point, for this reason. Then the vice versa is compared to carbon dioxide, let's say equally stable at both temperatures, but when the temperature goes down, this value goes down, this product goes down, then it's still negative but not that significantly or not that high compared to earlier. Earlier it was highly negative. Now with drop of this, the negativeness of this value, delta G value, would drop, would get decreased. Okay, compared to the stability of carbon monoxide at high temperatures, its stability at lower temperatures would be less. But carbon dioxide remains as it is. Its stability does not get changed with the temperature much. Therefore, compared to carbon monoxide, carbon dioxide we would call more stable at lower temperatures. So, hope you could understand the point that students, at high temperatures, carbon monoxide would be more stable, at lower temperatures, carbon dioxide would be more stable. Okay, this is very important. Then the tendency of carbon monoxide at high temperatures, carbon monoxide would be formed by the carbon dioxide here. So it's all of a sudden with this combustion reaction you got a huge amount of carbon dioxide formed, but the temperature is very high, therefore its transformation is spontaneous. It's very high the temperature, therefore at this high temperature, this carbon monoxide would get carbon dioxide would get transformed into carbon monoxide easily, smoothly, gradually. Then when it goes up, the temperature would drop, get decreased. With the reduction of temperature, now the stability of carbon dioxide compared to carbon monoxide get increased. Therefore, the natural tendency of this carbon monoxide going up is to transform into carbon dioxide. So you would get carbon monoxide being formed there at the bottom by the carbon dioxide already formed by this combustion reaction. So therefore, using carbon dioxide formed, carbon monoxide would be reformed. Means carbon dioxide formed would combine with coal as to form carbon monoxide. At the bottom you get carbon monoxide forming. This carbon monoxide going up with reduction of temperature, its stability drops, decreases. So its ability to get transformed into carbon dioxide get increased. So at the top the temperature is very low now, it's compared to the bottom. So it's now the carbon monoxide would start thinking, I will become carbon dioxide now. So carbon monoxide would get transformed into carbon dioxide. How? To carbon monoxide to be transformed into carbon dioxide, it needs another oxygen. It needs to reduce something. It needs to take oxygen from something. Anyway, it is, though you have passed air, all the oxygen was there in air was totally used up. That's why we maintain the coke amount as it's more than the required for this reaction. So it's excessively we use here coke. Therefore, we could say all the oxygen is anyway over. When carbon dioxide seeks its ways to get transformed into carbon monoxide, because when carbon monoxide seeks its own way to get transformed into carbon dioxide, having another oxygen, Oxygen is absent, O2 is absent, dioxygen is absent there. So it could see only this Fe2O3 or iron oxide. It's there, takes oxygen from iron, reducing iron oxide into its low oxygen states, finally into iron, metallic iron. That's how it works. Okay students, hope it's clear to you. So it's then act with changing of temperature, the stabilities of those two, carbon dioxide and carbon monoxide, would get changed. That's very, very important, deciding the abilities of them to reduce, especially carbon monoxide, to reduce iron oxide. So let me show you the change of their amounts, percentages of those carbon dioxide and carbon monoxide. Let's talk about carbon monoxide. Carbon monoxide percentage, changing of carbon monoxide percentage with temperature. Students, let's photograph as here it's the percentage. It is 20%, 40%, 60, 80, 100%. It is the percentage of carbon monoxide. Then here it's let's use this for temperature. It is 200. It is in centigrade. 200, 400, 600, 800, 1000, 1200, the temperature. So then you could find that when it reaches 1000, the temperature, it's almost all carbon dioxide would have transformed into carbon monoxide. Means the percentage of carbon monoxide could be found as 100. So then it's in this way you could find that varying. So students, it's the composition of carbon monoxide would get varied with the temperature in this manner. Carbon dioxide here would get transformed into carbon monoxide. So at lower temperatures you would have more carbon dioxide, less carbon monoxide. So it is this reaction would be proceeded. Carbon solid would combine with carbon dioxide gas, giving carbon monoxide gas. So at high temperatures, when it is close to 1000, 100% of carbon dioxide would have got transformed into carbon monoxide. So the stability, you would show that the stability of carbon monoxide and carbon dioxide there with respect to temperature. Students, at high temperatures, you could expect a greater carbon monoxide composition. And at lower temperatures, it is less the carbon monoxide and high the carbon dioxide. So that's why carbon monoxide then transforms into carbon dioxide at lower temperatures, giving the support, giving the required reduction power. Then I'm about to talk about these reduction reactions of coal. When this goes up with the reduction of temperature, with the reduction of stability of carbon monoxide, its ability to get transformed into carbon dioxide would get increased. Therefore, at the top, this carbon monoxide would find Fe2O3. It is ferric oxide. Then, with carbon monoxide, it transforms that into ferrous oxide first. It's not all of it. At the very top, it is just a part of it. Let's say 33.3% of ferric is got transformed into ferrous. It's a mixture of ferrous and ferric. We call that ferrosoferric oxide. It is Fe3O4 solid you get. Then carbon dioxide will be formed. The reaction is, it could be balanced, giving 2 here, 3 here. It is 6, then it is 9, it is 8. But the difference of oxygen here from carbon monoxide to carbon dioxide is 1. So it's the balanced chemical equation standing for the reduction of ferric oxide at the top. Halfway it gets transformed into ferrous. This carbon monoxide going up provides that force. Now it takes one oxygen from ferric as to transform into carbon dioxide. For the reason carbon dioxide is the stable one at lower temperatures. Then when it goes down, this ferrosulfuric oxide, Fe3O4, is having ferrous and ferric both. That's why we call it in that way. With further carbon monoxide would form ferrous oxide completely. So it further transforms into carbon dioxide. Then students, you have 3 here. Let's make that 6, giving this way. So it's 8 now, you get it's 6. Now the amount of oxygen, the difference is 2. When you make it 2 here and 2 here, the difference by 1 carbon monoxide to carbon dioxide transformation is 1 oxygen. So then it will give us 2 oxygen there. So you could write it either in this form or dividing that by 2, you could write it in the form as of Fe3O4 solid with CO gas giving 3FeO solid and CO2 gas. You could either give it in this way or this way, it doesn't matter. Okay, then students, it's at the bottom, this is at the mid, let's say, it's at the bottom you would get this reaction. It's formed FeO finally would react with carbon monoxide, the main reducing agent, becoming iron. It is, as we have already seen, it's a high temperature there and it's a genuine melting point of iron. Therefore, iron here formed is a liquid iron, is in its liquid form, not solid form. So, if you get carbon dioxide here as well, CO2. Then it is, you need to give 1 oxygen, it has already got balance. Student, in this way, carbon monoxide reduces ferric oxide, ferrous oxide at different sites. Okay. Then, as you have already seen, used limestone, calcium carbonate decomposed into carbon dioxide gas and calcium oxide solid. This carbon dioxide is formed by decomposition of calcium carbonate below 1000 degrees of centigrade. We have seen the temperature being 898 degrees of centigrade, the decomposition temperature. So it's possible below 1000 to have this reaction. It also provides you carbon dioxide. This carbon dioxide at this site could further react with coke as to provide more and more carbon monoxide. It also provides carbon monoxide. Anyway, the fate of all the carbon monoxide going up is the transformation of that into carbon dioxide. Therefore, students, it's finally you would expect more carbon dioxide here in the waste air. Anyway, it causes increase of carbon dioxide in the environment by this waste air. So in blast furnace, it's one of disadvantage environmentally. So we need to seek some options as to reduce this carbon dioxide yield or waste. Anyway, it's at the bottom, having this high temperature, the reactions could take place there at the bottom are, it's once coke could be burned in O2 giving carbon dioxide. It's an exothermic reaction, it provides the required temperature or it maintains the temperature at the bottom at a high value. Then students, you could have this reaction as well at the bottom. Ferrous oxide would be transformed by coke into iron liquid. But it's another reduction reaction. Though it is not the main reducing agent, carbon monoxide is the main reducing agent. Carbon itself, though it is not the main reducing agent, it serves here as the reducing agent, and it reduces ferrous oxide into iron. Then it's another reaction possible. It is quite disadvantageous. Its oxygen could combine with carbon monoxide, giving you carbon dioxide. So it's quite disadvantageous, and if you provide more air, means if the rate of air supply is greater than it requires, we could have this reaction also at the bottom. So it reduces the amount of carbon monoxide which provides our driving force for the reaction. Therefore, we need to avoid having this reaction. Therefore, we need to make that sure. Now you get the point. We need to make that sure our coke amount is greater than of its required amount for the reaction here, this reaction. So we expect all the oxygen here to be used up and no oxygen remains for this reaction. This is quite disadvantageous. This reduces our carbon monoxide, then it drops the efficiency of this reduction process. Then students, you need to know those stuff. And as you have already seen, this calcium oxide could combine with silica, SiO2 forming calcium silicate, CaSiO3, and could combine with alumina, Al2O3 forming CaAlO2 twice, calcium silicate and calcium aluminate form this slag. It's less dense than liquid iron, as well as it also is at a greater temperature now, means its melting point would be lesser than of this high temperature. It also at its liquid state. Therefore, students, it's possible that this also, those calcium silicate, calcium aluminate also to be formed at its liquid state, which would then float at the liquid iron and covers that form molten iron or liquid iron from the oxygen contact. So it's very, very important. Okay, hope those points are clear to you. It's then students, further, what you get here is the liquid iron. When it is solidifies there, we call it raw iron or pig iron. So it's having a very high carbon percentage in it. It's this pig iron or raw iron is having a roughly 4% of carbon in it. Then students, it's having further some other impurities are manganese, raw iron or pig iron, having manganese, silicon, phosphorus, sulfur as the other impurities. Then if we could heat this raw iron, this pig iron with calcium oxide as to transform that into cast iron. Cast iron is having a 2.5 to 4% or let's say 3% of carbon. Then it is used there in pipes and gates and such appliances. Then students, you could heat or you could melt this pig iron and blow cooled oxygen stream through that, means air stream through that, as to reduce the amount of impurities. When you pass cold air stream there, those impurities would get rid. Means sulfur would turn into sulfur dioxide, silicon into silicon dioxide, phosphorus into its oxide, So in that way, you could reduce those impurities, remove those impurities. Then students, you could manufacture steel. It is the other one, steel. When you consider steel, it's having 0.05 to 1.7% of carbon there in steel. So there are different qualities of steel. So high quality, mid quality or average quality steel you could find there. Then students, if you could dope some other elements, metals as well as to manufacture stainless steel. In stainless steel, you would expect 73% of iron and it is 18% of chromium and it is 8% of nickel as well as finally 1% of carbon. So you could use stainless steel in those cutleries and wristwatches and various such appliances. You could apply steel there in vehicles and many others like kitchen knives and such appliances. Then students, if you could further purify this iron, when you heat pig iron with Fe2O3 ferric oxide, you would get more pure iron. It is 99.5% pure iron. We call that iron 99.5% pure iron. You would get. It is wrought iron. Wrought iron is good at casting. Therefore, is used to manufacture those constructions, things like bridges, those some such constructions things. In those, it's easy to cast there. Okay, those are the applications of those various types of irons. Then students, it's these things you need to know regarding the iron industry, iron and steel manufacturing industry. It is important knowing these things as to find some options as to reduce this carbon dioxide amount there, as to reduce the environmental impact. Then it's recommended using less amount of iron containing substance, means iron composition consumption, for the reason it contributes in one hand to the environmental pollution, releasing carbon dioxide, and by the heat also it could result some environmental pollution. Anyway, those are the stuff that you need to know regarding iron industry. So it's with the hope as to meet you with another chemical industry, we are going to round up here in this video. Okay students, it's goodbye.